Non-US Saturday from Swinging Place.
Thanks, Nick. Thanks for coming. Can you hear me in the back? All right, so I'd like to talk about non-US Saturday and string inflation, and I'm going to first use the mandatory bond joke at the very beginning here that there's a seat at 25 and bond at 60. That's actually, I brought along the movie Russia Would Love It if we run out of time here. I thought that'd be over here. So in an audience like this, it's always intimidating because I might not cite you, so there you are. But really, I should say that because I know that what I'm going to talk about is something which was dear to his heart. So he was interested in trying to in string inflation models to imagine pretty much everybody generates remarkable fluctuations in the vanilla inflaton way. And I know that Lev was interested very much in other mechanisms that would play a role in that, and he proposed one of the mechanisms, the modulation mechanism, whereby some physics other than adiabatic fluctuations and string inflation gets processed in the post-inflationary epoch into adiabatic fluctuations, and that's what we actually see. That's something which is, as you'll see, useful in string inflation because the parameters of the model, like the string scale, are being dialed to make the amplitude, for instance, of the remarkable fluctuation the right one. And the string scale you're led to is not so useful for other applications, like if you wanted to know what the supersymmetry breaking scale is, that's also part of the string scale. And so there's a tension between what cosmology wants and what the rest of physics wants, and what's nice about string inflation is exactly that. It's a theory of everything, and so you have to get it all right, not just some little piece of your dogma microwave background right. So Lev was a pioneer in this area, and I know he was interested in the last year in trying to realize it in a concrete string inflation model. And what I'd like to describe is a concrete realization of a non-standard, non-vanilla inflaton mechanism for generating fluctuations in a string concrete. So let me give you a couple slides of why you're here. The one we actually get in the cosmology practice is you describe these models and it sounds really baroque. And all you're trying to describe is something very simple. Why would you go to such lengths? And so I want to motivate that because there are reasons. I'll tell you about the specific model, which is in the context of large volume modulus stabilization in the string theory. And I'll tell you why those are very interesting in their own right, but also why they're natural framework in which to think about inflation. And then I'll sketch the curvaton. The mechanism I'm going to produce is a curvaton mechanism, but it's an example. And probably the lesson to be drawn, the most important thing to get from this is that you're going to find that this mechanism is going to work. I'm going to produce non-Gaussianity for you because it's a non-single field vanilla mechanism. But should you see non-Gaussianity in the CMB, and if it's a long, thin triangle piece, probably the real thing that we learn from that is that the dynamics driving inflation or responsible for these fluctuations is some multi-field combination. And it doesn't mean it's going to be the model I showed you. It doesn't mean it's going to be the same way it doesn't mean it's vectorial. It's just the way that physics at high scales influences inflation, the way we understand it now, tends to be through four-dimensional field theories. And the best we can hope to get from the data is a sense of what that four-dimensional dynamics is. And it won't be a direct smoking gun for the more microscopic physics. So, why make these models? So, inflation is pointing to, if you buy that inflation is describing the pattern of fluctuation you see in the CMB, then the scales involved are quite plausibly large, and they're comparable, though lower than the scale of gravity. And the interplay, what makes it a useful interplay to try and connect inflationary observations to something as baroque as string theory, is that there is actual information transfer back and forth. It's not easy to make a model that gives you inflation that you can embed into something like string theory, and because it's not easy, you might hope that of all the various models that you could hope to try and be describe the data with, there's a subset that you can be taken seriously, given that you have another piece of information coming from other areas of physics, like quantum gravity or particle physics, that constrain your choices. So the kinds of things that you'd like to learn about inflation from string theory, there are things you can learn about string theory from inflation, but this is what I'd like to talk about is what you can learn from inflation from string theory. You'd like to ask, is it generically as hard to get inflation in string theory as it is in other theories? Flat potentials are what you're living off of, and those are notoriously sensitive to ultraviolet physics. the string theory give you a different picture of that. And in particular, the important thing here for the people that don't like these models is in an inflationary model, the hard work is not in the model you write down, it's the model you don't write down. It's the things that could have screwed up your inflation, which tend to be very small things like Planck's law, that are dangerous for these inflationary models. And the point of these stringing exercises is to control your calculation, to show what you have, but also what you don't have, so you really can reliably draw the inflationary conclusions. And that's rarely done with a simple, vanilla cosmological model. So because you're really making contact with microscopic physics, it's not enough to have some crappy old model that just describes it. One thing that you know that's relevant for the story of curvatons and how does reheating work is more generically an example of the kind of question that you can't address unless you know the full microphysics of this energy scale that are relevant to inflation. Because the story of reheating is how does the energy from inflation get into the standard model degrees of freedom, but also why does it not go into the other degrees of freedom that you don't care about in the standard model that may be there. So there's an insulation problem as well as a furnace problem in reheating. And you can't even address that unless you know what all the degrees of freedom are, and the first framework that we have for doing that is the string chemical framework. I'd like to note there's specifically stringy implications, and I'm not going to talk about those. So. Now, for the purpose of what I want to say in the rest of the talk, what you need to know about the various models that have been looked at, and we're at the surveying stage still. People are kind of fishing around in the solutions of time-dependent string configurations, which are hard to find. And generically, they're only found in a four-dimensional limit, looking for inflationary solutions to try and find what the patterns are. And what's typical of most of the ones that have been found is that once you find there are lots of fields that are there, and then some field is rolling around in some multi-dimensional field space, but when push comes to shove, it's just the standard inflaton kind of description that's going on because fields aren't making any sharp turns or anything as they go through horizon exit. And so you're not getting any isocurvature perturbations. And that's partly because that's what people have been looking for. And people look for that because that keeps the answer very robust and not sensitive to the post-inflationary dynamics. Now, one of the things that I alluded to before was that the string scale is being pinned down by with that choice, you have a specific kind of relationship between parameters and what you see in the sky. Now, if we're looking for other mechanisms, the kind of things you're looking for are, you're opening up this can of worms that you will now have to care a little bit in more detail about what happens after inflation to decide what the temperature fluctuations are that you should see at very late times. That's the bad part. The good part is that that's worth doing if you think you have an observational handle on that. If you think that something like non-Gaussianity is telling you about that kind of dynamics, then you want to know what your sensitivity is because you may be learning about that kind of dynamics observationally, and of course, predictions are what you have to compare to. So you really want to explore those things. The trick is always to find these light fields, because having inflation itself required having an inflaton that was very light compared to the Hubble scale at the time. And these other fields, these other mechanisms rely on there being other fields that fluctuate during inflation. And so they have to be lighter than the Hubble scale during inflation. So you have isocurvature fluctuations, and then some post-inflationary process turns that into a mathematic fluctuation. And that's what we see in the sky later on. So the trick is how you find light fields, and that guides how you look in the space of vacuum. So how do you look in the space of vacuum? The first thing you have to do is identify some fields and what their scalar potential is. And so I want to look into what's called the large volume scenario. And so I'll first tell you about what that scenario is, and then tell you about how inflation works, which is not so complicated in that scenario. So the way the scenario works is, it's in this context. You've probably seen the picture before. The baroqueness in these models comes from the fact that you have 10 dimensions at the end of the day, and those extra dimensions are described effectively by scalar fields. And until about 10 years ago, people didn't really know how to tell you what the energy cost was of deforming the extra dimensions. And what happened about 10 years ago was an understanding, a calculable understanding of that was developed, whereby an arrangement of branes and fluxes and the extra dimensions made them stiff against changing shape. So if you think about a sphere and a monopole on the inside, spreading the sphere, that is the kind of thing that makes changing the size of the sphere difficult, because gravity likes the sphere to implode, but that would also take the quantized magnetic flux, and since the flux is quantized, the field strength would have to grow if you make the sphere smaller, and that costs you an energy which makes enough on a strength, and so the balance can stabilize the size of extra dimensions in that way. And so typically you've got 6 extra dimensions, you have more than just the volume, you've got a whole bunch of different shape variables, and they're all described by potential, and that's calculable in some regimes based on this kind of flux idea in this specific kind of context. Now, the large volume scenario is a specific subset of these applications which looks for solutions minimize this potential out at very, very large volumes compared to the string size. And the surprise was that, the surprise was on the next slide, when the volume is large, what's nice about that is that the potential you're trying to calculate can be approximated as a series in one over the volume. And so there are two kinds of corrections to follow. There's the string perturbation theory corrections, the string Huntley constant powers of that. There's also the 1 over volume corrections coming from the fact that you're looking at low energies compared to the string scale, and so you're doing a curvature, a low derivative expansion compared to the string scale. Those things assemble themselves into potential, which comes hierarchically to you as powers of volume. And the surprising observation that these people made when they found this, they proposed this scenario was that if you have a small modulus describing a little, nipple on your dimensions that it can change its shape independently of the whole volume, that tends to balance, can be used to stabilize the entire volume of the extra dimensions, because the potential has this form. If tau sub s is the thing describing the small little bubble on the extra dimensions, and v is the volume, the shape of the potential at large volume has this particular form, where you're looking at a regime where the volume is comparable to the exponential of the size of this little bubble on the side of the extra dimensions. And so all three of those terms are the same size, even though they have different powers of volume, because they're counterbalanced by different powers of this exponential size of this small piece. And that potential has a minimum, where both those fields are stabilized. The small piece is stabilized at a comparatively small value, one over the string size, so it's big enough that you can trust the calculation. But the volume is exponentially larger than that. So a small change in the parameters of your theory gives you a wide range of volumes, so that the A in that formula is something which you get to adjust by choosing flexibility volume. So you have a huge range of volumes you can choose from. And the potential is coming to you for all these potentials, as a function of these variables, organized in powers of 1 over volume. So what I just described was the U-naught piece in the potential, but subdominant to that are other moduli that could be large, which I'm calling Km or Km moduli. That could be a little bit smaller. It's parametrically smaller as a function of the size of the other moduli, which are describing other shapes in the extra dimensions. String loops give you something that comes in at the order of 1 over v to the 10 third, it turns out. And so you have a systematic suppression of higher contributions by powers of 1 over volume. And the important part for inflation is that the leading terms in that series don't depend on a lot of the fields. And so that means that for those corrections, it's a very flat potential. So that's the way we're going to make inflation. So we'll start off with that thing. The first term is what's stabilizing the volume. We'll look for somebody who's in the second term who's going to like to be comparatively flat compared to the first term. And that's called the Taylor modulus inflation scenario. And so what happens there is, it's easy to think about if you think about what would happen if you just followed a radius and you just thought about what Einstein's action tells you about the energy of changing the size of an extra dimension. You get a kinetic term coming from the Einstein term, which then sees derivatives of this radius in the space-time directions, and then you get a potential energy, which is typically some series in 1 over the volume. And because the kinetic term is not canonical, there's a 1 over r squared in front of the kinetic energy. That means that the log of the radius is the canonical variable. So what you find is what's typically an exponential potential if you write it in terms of the canonical variables. And inflation loves those kind of things. See if you can get a constant piece, which is the tricky part. Because the slow roll parameters are exponentials. The further you go out in field space, the more you like it. The flatter it is. And if you ask what does that mean geometrically to have phi be large, it means that your radius is large compared to the Planck scale, or the string scale, and that's where you believe your calculations. So the main validity of the approximations is where the potential likes to be flat, and it's nice to be models. And so this kind of an inflationary model gives you predictions for the gravitational waves, which is kind of smallish but potentially observable, because there's a natural hierarchy that relates epsilon and eta squared, the eta, the two slow parameters. And in that model, the way we're going to try and get the curvaton is, you've got other things. There are many moduli are in the first two terms, they first appear in the third term. And so their masses will be parametrically small compared to the Hubble scale, which I just described to you as coming from this first term as being going like the volume of -3/2. The mass of things coming from this last U-loop term have masses going like 1 over volume to the 5/3 or something like that. So it's parametrically small compared to the Hubble scale. So those are the guys we're going to look for to be curvatons. They're what you need it to be. They're light on the inflationary scale. So what you need for curvaton, the curvaton mechanism, like quantum and company, is you're looking for some isocurvature mode that be fluctuating during inflation. After inflation, what you like to have is the inflaton dumps its energy into the observable sector at some point, And then at some later point, the curvaton field that has some fluctuations occurring on it starts to oscillate because eventually the Hubble scale comes down to its mass. So it oscillates, and during the oscillation time, it behaves like its energy scales like non-relativistic matter. And so the relative fraction of energy in that compared to the radiation starts to grow because the radiation is falling faster. And then at some point, you'd like the curvaton to then decay, and it releases its energy into what will be ultimately the temperature we see at big time. And that's how it works. So I have to show you that you get these things. And so because Neil is here, I'll show you very quickly. I told you with mass already. It turns out the decay rates are governed by the couplings, which are predicted as functions of the volume. And there's a hierarchy to the bottom there. I'm not going to be longer. These fields do live longer. And they do. Bottom line is, you get something like a fraction of order, a tenth or a hundredth of the natural range for the fraction in the curvaton, and that tends to give you Gaussianities in the ballpark of 60. 50, 10, 50, 100, in that range. So what's the bottom line? Let me just go to the photo slide. Bottom line is that these large volume potentials are very interesting from the point of view of many things, naturalists in general, but things that like flat potentials are like these models, and these models like them back. And so it's a good place to think about inflation. It naturally provides lots and lots of fields, which will like to be fluctuating in a cosmologically interesting way as inflation happens and as the later epochs come around. Given that, it turns out that the couplings and masses of those fields have what you would need to be a curvaton. They need it, but they can if you use the potential property. So should you find non-Gaussianity, what you're probably seeing is some multi-field with long thin triangles, because it's late times. You're probably seeing some multi-field dynamics, which could be this, or it could be some other microscopic physics. Thank you for your attention.
Questions?
So I have a question. So, do you call these models natural?
Technically, that's what I mean.
Well, what are you consider natural?
This particular physics model that I use, I didn't mention, I'm kind of unbiased. I think they're less natural than one time.
But still.
I think they're as good as you get in the extreme. It's better than they so far.
I have a nice question.
Oh, it's the combination of the signals. The way that you that's partly compensated by the fact that the so
So this can happen in these models. It's a generic. We always get detectable on this. I mean, if we don't see it, can we say that we ruled out one?
No, I wish you could. It's one of these things that it's still fishing, and no one really knows what the real landscape is, but they were a little bit hard to find when you start.
But I mean, it's not, so if this is the type of relation, you can't say you definitely have a large enough network.
No, I think.
Take many people to we are 11 come to use that things I'm down to like 10%, so I wouldn't know. Sorry? Use your thing.
A year.
Electronic. It's question more. Not GDM.
since PowerPoint.
Because we just went electronic this last year, and that was a lot of fun
Okay.
too.
If this doesn't work, then then I can probably do a Blackboard talk.
Right.
And it's that.
Do we want to make a last ditch effort to try and switch computers, or do we want to?
No, that I don't want to decide next to that.
Implications with other audiences as well.
Okay, so the next speaker will be continuing the perimeter session of the afternoon. Will be Niayesh Afshordi, and he will either be giving us a presentation or an impromptu Blackboard.
Yeah. So I know that something is happening there because I can see my mouse pointer. But let's get it started. So where is the light here? This one. No. Good. Okay. Perfect. So so sorry that this doesn't seem to be working. I guess this is another reason to switch from Windows to Apple.
Here.
On the next to the faucets.
There you go. Thanks. So I want to tell you about. So this is what I'm going to tell you. I'm going to tell you about the connection between dark energy. Now I'm a cosmologist by training. So one thing that I did for my thesis, something's happening.
I want the Blackboard talk.
Half and half.
Okay, we can do that. But let's see. So ignore that screen.
You do both?
We can do both. So naturally, that I guess most of us agree that one of the most exciting things that happened in cosmology over the past decade, or over the current century, has been dark energy. Now, that being said, and I wrote down that for my thesis, and I worked on observation of signatures of dark energy. But now I'm at the Perimeter Institute. And at Perimeter Institute, people are somewhat different interests. So quantum gravity is the name that often goes with the Perimeter Institute. And that's a hot topic there. And I actually did an ADS search, and that's the thing that you almost think that actually. See. Anyway, so there are 4,000 and I think 300 papers on ADS with the title dark energy in the and with the name dark energy in their title.
How many of them are good?
But that ADS cannot tell you, but I think the next version is ADS Premium. So quantum gravity is a much older subject. Maybe I think it's 4,100 now. Quantum gravity is a much older subject. It's probably 70 years old. But it's only slightly more papers than this, maybe around 4,300. And the other subject, which is kind of interesting, is black hole entropy. And that is also, as you can imagine, this is much older than dark energy, not quite as popular, but about 1,200 papers in this. Now there are actually, so these are all important areas in theoretical physics. Oh, okay, good, I don't have to. So, okay, good. So, I mean, if it ever comes around, yeah. So I did a literature search, and so this is roughly the numbers that I wrote for you, and these are all very, very hot topics in theoretical physics. However, there isn't much commonplace between these these topics, it seems that there's the two that you think have most in common is quantum gravity and black hole entropy, and there are only 40 papers that have both of them in their titles. Among dark energy and quantum gravity, there are 5 papers, and in dark energy and black hole entropy, there are 2 papers. And okay, so this long introduction comes to an end. There is only one paper which has all 3 of these words in the title, and that's what I'm going to talk about. So why would the cosmologists care about quantum gravity? So there are actually good reasons. So people think about quantum gravity often as a problem in high-energy physics or extremely high-energy physics. But there is actually there is a cosmologist's quantum gravity problem. So there is, so what time do you start? 5 minutes ago, thank you. However, of course, all of us know that there is one big problem in cosmology, there is singularity. Big Bang singularity. And Big Bang. That is a problem in cosmology, but we seem to think that quantum gravity is the only way to solve it, and that probably goes to the heart of the problem in quantum gravity, which is non-realizability. Although we have no proof that this is the fix, but we hope that this is going to fix the problem. The other parts of quantum gravity problem that people often ignore, and is most important for cosmologists, is the cosmological constant problem. And indeed, so people often put these quantum gravity and cosmological constant problems in different categories. But the fact is that cosmological constant problem is a problem of quantum gravity because it comes from measure of quantum mechanics coupled to gravity. And of course, I don't have to tell you that there are different versions of this. The old version has been with us since Pauli from 1920s, and that's the fact that rho vacuum is not 10 to the 33 kilograms per meter cubed. In fact, it's much smaller than that. This is the old one, and the new one is the fact that this is roughly 10 to the minus 27 kilogram per meter cubed, which is measured with 10% accuracy. Now, I'm not writing the numbers here, but we know this to 10% accuracy. And then this third aspect of the problem, which is, there's old, there is new, and then there's a coincidence problem. That somehow this rho vacuum happens to be observable now. So the age of the universe, when vacuum dominates, is the same as the age of the universe when intelligent life happens to exist. So that's okay. So let me just remind myself. So this is, at least this is my motivation for why cosmology. This is cosmologist's motivation for caring about the quantum gravity. So indeed, it may not have been the wrong career for me to move to the Parameter Institute after all. Now, so what are the approaches to quantum gravity, and how does that concern cosmology? That I'm not going to list them for you. There are things like a string theory. Remember here, since I'm at parameters, we talk about loop quantum gravity. At least I should mention it. And there are other ones. There is one that I believe is cosmology's favorite, and it's known as emergent gravity. It has different names. But one of the common features in this general area of emergent gravity is that Lorentz symmetry or the finite version of that, which is for the covariance or diffeomorphism invariance, are not fundamental symmetries of nature. So they are emergent at low energies, but at the fundamental high energy level, these are not requirements for a theory of that. Now, why is that a cosmologist's favorite? In my opinion, the reason that's cosmologist's favorite is that universe, as we see it, is not Lorentz invariant. If you look at the universe on larger scales, it is homogeneous. So it has 3D diffeomorphism invariance. In other words, it has translation invariance in space and it has rotational invariance. So the universe is homogeneous and isotropic, but it does vary with time. So it seems that the Lorentz symmetry is broken at some level somewhere in the history of the universe. And our universe doesn't look very symmetric on larger scales. So maybe it's actually broken at the fundamental level. If you go through every time the fundamental universe, there is indeed a preferred frame. So I think this is what I call cosmology's favorite. Because our universe on larger scale looks 3D diffeomorphism invariant, but not 4D diffeomorphism invariant. And there is, in the line of, related to this is so-called Kojava's proposal, which has been very popular over the past couple of years, which indeed does that and shows that gravity is renormalizable if you break the 4D diffeomorphism invariance at the fundamental level. 5 minutes. Thank you. Okay, so that's good. So what's the implication? So here's the question now. Let's say that we buy this line of thought and think that Lorentz invariance is not fundamental. So that means that there is a preferred frame, and you can always think of a preferred frame as ether or a fluid that fills the universe. It's not really that different from inflaton or dark energy that are now nowadays popular in cosmology literature. You just have an extra fluid. And the thing is that at low energies, this is only important for quantum gravity. At low energies, you don't see this fluid. You are essentially decoupled from it. But at high energies, because it's a component of a renormalizable theory of gravity, at high energies, you have to couple to it for gravity to make sense. Now, if you have a fluid, it could have a pressure. And if pressure, we know at the classical level, it should vanish. But we know we have non-classical objects in the universe. In particular, we have black holes. And they have singularities. So gravity cannot be, if you want to make sense of black holes, gravity cannot be classical. Moreover, you have broken Lorentz invariance. So horizons are no more at the fundamental level. It's the Lorentz invariance that tells us that censors singularities. But if you say that Lorentz invariance is not fundamental, you could have a speed of propagation that's larger than Mach. Indeed, that's the case in Kojava's theory of gravity. The speed of propagation goes to infinity. So singularities, or in other words, quantum gravity, can affect everyday life. Now, so that's the motivation. And so in the last 3 minutes, let me just point out an interesting coincidence that if you believe this train of thought, this line of thought, you can actually justify it. So black hole thermodynamics, that's a framework that we have to describe properties of black holes. Entropy of black hole goes as area, which is roughly 1 over temperature squared. And mass of black hole goes as surface gravity, which is roughly which is defined to be 1/temperature. So this is the standard in general relativity of black holes. But of course, if you have quantum gravity, you expect modifications of modifications to this. So there would be terms like alpha times temperature divided by m Planck, plus terms, let's say alpha 2 T squared divided by m Planck squared. And the same goes with this mass temperature relationship. And I'm talking here about non-rotating spherical black holes. So basically, you have corrections that are suppressed by Planck mass. Remember, I also told you that there's a fluid in the universe, which quantifies that preferred frame. One thing we know about thermodynamics is, and all of you remember from freshman physics, is that you can actually put these. So this is the mass, which is the same as energy. Put this into this relationship and get a pressure. To zeroth order in Planck, you know you get zero pressure. That's how black hole thermodynamics is defined. There is no pressure. But these corrections can give you a pressure. Indeed, they do. If you just plug those relationships in here, the pressure is alpha pi temperature Q times m Planck. If I want to be dimensionally correct, there is an m Planck squared here, and there is an m Planck squared. Notice that this pressure doesn't go as temperature to the 4th power, it goes as cube of temperature. So it's much bigger than the pressure of Hawking radiation. And even more interestingly, if I put in real numbers here, this is minus alpha mass divided by 60 solar mass to the third minus 3 power. So temperature is a function of mass, of course. So sorry, there is no minus. So, sorry, there is yes, something missing. This is rho dark energy of 0. So for 60 solar mass black hole, if alpha was 1, the pressure that you get from thermodynamic first law is the same as dark energy pressure. So the fact that we know that masses of black holes in the universe are over the 10 solar masses, so indeed you have a precision measurement for alpha if you believe this line of argument, and there isn't much of it, it's just this. Alpha becomes something like minus 0.03, I believe, plus or minus some small number. It's say masses around 10 solar mass. And we know that most of the black holes are around 10 solar mass because most of the black holes in the universe are stellar black holes. So I'm going to leave you with this intriguing possibility, at least in my opinion, intriguing possibility that the measurement of dark energy is the first precision measurement in quantum gravity, as is in fact measuring the first correction to the entropy of black holes.